Hello students, welcome to class 17. Okay, so we will continue with regarding the oxidative addition and reductive elimination concepts, okay, or insertion. So like this, so from the previous videos. Okay, so in the last videos I think I had discussed with some of the Agostic type of elimination, Agostic reactions, beta eliminations, okay, and the features for the eliminations. These all things we are learning: beta hydride eliminations, features, different features. So this thing you have to keep in the mind: the different features for oxidative addition, different features for the what do you say, that reductive eliminations, features for beta hydride eliminations, features for migratory insertions. These all things you have to keep in the mind. Okay, so that will help you to solve the problems. Okay, now for example, in one case I have seen that in one paper they had asked in competitive examinations this question here: PPH3 and this is PPH3. Okay, so where this is a square planar structure, okay, 16 electron complex, square planar 16 electron complex, COCl type Osaka's complex type. Okay, so this when heated in the presence of decalin intermediate. Okay, so this is going to form like this. Okay, so iridium is there, then ClH PPH3, okay, and P something like that is given. Okay, like this, pH2. Okay, then 1 2 3 1 2 PPH3 3 like this. Okay, so octahedral complex when iridium is we'll see that. Okay, and now see here, so this is what question is, and he will give you four options: A, B, C, D. Okay, so this reaction undergoes oxidative addition, reductive elimination, so hydride elimination, hydride addition, something like that. Okay, so four options will be there, so we have to identify the correct one here. So first one will go that whether it is oxidative addition or what. Okay, so yeah, definitely if you see here, so it is square planar 16 electron and it is in +1 oxidation state because all three are neutral, and here minus +1, and here you can see here it is 1 2 and phenyl group is attached here 3, so +3 oxidation state definitely. So this reaction is oxidative addition because there is change in the oxidation state of iridium from +1 to +3, so it's oxidative addition reaction. This is correct. Now second is beta hydride elimination. So whether this is beta hydride elimination, so hydride elimination is there, so here beta, so because hydrogen is separately he has attached here, so he may ask beta, so students may go for yes, it is a beta hydride elimination because it is eliminated, then so it's not like that. So it is a Agostic type of, as I said in the previous class. So this is somewhat like this. Okay, PH2 is there, and one of the ring I split it here in this way, and here it is joined, and one of the hydrogen is joined in this way. Okay, and PPH3 something like that. Okay, and this type of reaction, what we call it as a Agostic reaction. Okay, where hydrogen and the carbon of this are simultaneously bonded to this iridium, and the next step it will be that, so this will break and it will form a separate bond here like this. Okay, and this is what the mechanism or something can be shown here like this, and it becomes coordinated. So from 4 to 6 coordinated, 4 5 6, so this one and this one will be separated, so 6 coordinated, so coordination number becomes here 6, and it is going to have +3 oxidation status. So that's why this we cannot call it as a beta hydride elimination. This is not a beta hydride elimination, so this is a Agostic reactions here. Okay, so that's why this is not beta hydride elimination. This thing you have to keep in the mind. Okay, so this concept is not a beta hydride eliminations. Okay, now next is what magnetic property you have to keep in the mind. So usually for 5D higher atomic structure here, iridium and all 5D 4D, so usually if you go for high atomic masses, this one, so definitely they are having the low spin complex always, not like 3D, so they may show low spin high spin, but these usually 5D elements or 4D, so usually they show low spin only, and they are diamagnetic in nature. they are diamagnetic in nature. So no doubt, no, if you try to go for the counting, and if you go for the value VBT or some other way also, so definitely it will be in diamagnetic nature. So that's why both the complex will be diamagnetic in nature usually. So no need. So if we go for higher 5D series, definitely all the elements are diamagnetic, low spin found, and that's why they are diamagnetic nature. So both are diamagnetic in nature. Okay, so this is what about the third concept you have to keep in the mind. Okay, so one is it is oxidative addition, it's not a beta hydride elimination, it's both are diamagnetic. So yeah, both are diamagnetic, so both are diamagnetic in nature. One more, migratory insertion, whether it is a migratory insertion or not. Okay, so you have to see migratory insertion, so you have to see this. For migratory insertion, the complex should be saturated, is it right? So you have to see this migratory. So this is 16 electron complex. So one of the favorable concept for migratory relaxation is what? It should be saturated. That means 18 electron. But we have started with what? 16 electron. Then there is no such dissociation or something in this case. So that's why it is not a migratory insertion. So this reaction is not a migratory insertion. Okay, so this is what you have to keep in the mind and solve the question. This was asked in net examination, giving these four options. Okay, and you have to write this. A, B, C, A, B is correct, C is wrong, like this. So I have told you the correct options here, so you can note on that and make it a point. Okay, now if you go for some other concepts here, okay, like Ravi had asked me one question in the Zoom that, sir, Fe0 and what is that? He asked me CO1 and Ni2. Okay, so in this, sir, Fe0 is greater than this, oxidative addition. Okay, so he asked me, Ravi asked me that, sir, Fe0 is there and this is Ni plus to Ni is having more electrons, like this. Okay, and one of the favorable condition for oxidative addition is what? Number of electrons. So number of electrons should be more. So he asked that. So I said that, yeah, plus 2, if you consider this oxidation state, definitely. Okay, so this is more oxidation state of this is more, then definitely oxidative addition will be less in this. Okay, so in that way I told you. But see, for oxidative addition, what is the condition? So condition is it has to oxidize from 1 to 2 year. Okay, so this condition is there. Now Fe0 is there, so Fe0 can be oxidized to Fe plus 3. So this is or plus 2. Okay, so this is favorable for plus 2 unit. Now Ni2 is there, so always Ni2 is there. Now if it wants to oxidize, it has to go for Ni plus 4 here. It plus 2 changes. Is it possible? It is possible, but this is not possible. Okay, Ni plus 4 is not stable, and that's why this will not undergo oxidation so nicely than this. Okay, so this is easily oxidized to plus 2. Definitely it will go. Plus 1 can be oxidized to plus 3. This will go, and finally this. This is rarest. Why? Because 2 cannot be again oxidized to 4. So that is why this order will be considered. Okay, if they ask in the examination. So this thing you have to, a nice question asked by Mr. Ravi. Okay, so this is what you can make a point of this. Next. And even 3D orbitals, because of very diffused in nature. Okay, so 3D orbitals are very diffused than the 4D and 5D, and that's why you can see that these are faster. 5D like iridium and whatever we are learning, the oxidative additions will be faster. So this also they will ask in some of the cases. So this also you can keep in the mind. Next is what one concept comes here is binuclear. Okay, binuclear oxidative addition. Binuclear oxidative addition. What is this binuclear oxidative addition? So here sharing will be there. So here what happens here, each of the two metal changes their oxidation state here. So each of two metal, okay, each of two metal changes its oxidation state. Okay, electron count and coordination number by how many? 1 unit is here. Okay, so in binuclear oxidative addition, so each of the two metal changes oxidation state, electron count, coordination number by 1 unit. So they are sharing there. Okay, they will share here. So like for example, if I take this ligand here, two metal, and if XY incoming ligand, if I want to oxidative addition here, so OA, so what will happen here? I am going to find ln X, ln M, sorry, X, ln M, Y, like this. I am going to form like this. Okay, so this is having plus 1 oxidation state, this will having plus 1 oxidation state in that way. Okay, so this is how, and this is shown by the 17 electron species. Okay, 1 electron extra, 17 electron, that is 16, but this is 17 electron species. Okay, so this type of this we call it as a binuclear oxidative addition, where the metal is sharing, two of the metal is going to share the oxidation state, coordination number and electron count by 1 unit. Okay, so in this way, so when I want to add this xy here, so I am going to get separately, that is ln x bond and ln y bond, like this. Okay, so this type of this we call it as what, oxidative binuclear oxidative addition. So this also you have to keep in the mind. Now in this mechanism of this oxidative addition, okay, we have learned concerted mechanism, we have learned SN2 mechanism, that is stepwise mechanism. Okay, these two I said it is very much important, these two. Okay, you have to keep in the mind. Concentrated you have learned with polar and non-polar, that is H2 and CH3 addition. Okay, and which is going to form like transition state, 3 side transition state. So you see that. Okay, SN2 I have shown that also, that is your addition of the CH3I here, SN2 mechanism. And one more is there here, so today we will brush up that also, which is not so much important, that is radical mechanism. Okay, a radical mechanism here. So so these are of two types here, non-chain and chain. Okay, so non-chain and chain mechanism. So if you see for non-chain, first one, okay, non-chain mechanism, non-chain and chain here, so radical mechanism. So this is non-chain mechanism, addition of the alkyl halide is taken place to the complex PPH3 thrice. This will show, okay, addition of alkyl halide to platinum triphenyl phosphine here. So we will see that in this way. So it is in 0 state here, PPH3, PH3, PPH3. So platinum is in 0 state here. So what happens in first state? Okay, this is a fast reaction. So platinum will be 0, PPH3, PPH3, like this. Okay, plus PPH3 will be out here. One of the ligand will be, I will write here, minus PPH3, and I am going to get this one. Okay, so platinum is in 0 state only here. Now this compound, this complex will be treated with phenyl bromide. Okay, alkyl bromide, aryl bromide type phenyl bromide. Okay, and which is a slow step here. So so what will happen now here? So I am going to get here, so this will abstract a proton. Now this compound is going to abstract abstract a proton now, and I am going to get this compound here, PT PH3 H P PH3, like this, something like that. Okay, so one of the, this is abstracted here, H. Okay, and this becomes +1. Now this platinum becomes +1, and I am going to get, this is abstracted one proton here, so I am going to get here PH PH PR, like this. Okay, so since one electron is abstracted, so I am going to get this one. See, this is a radical chain. Okay, I got it here in this way. Okay, like this. PH CH Br, PH CH PH CH Br, like this. Like this I am going to get. So one of the hydrogen is abstracted here. Okay, that is PH CH2 is there, no? So one of the hydrogen is abstracted here, like this, and it is going to form radical in this way. Okay, so this plus this we are going to get like this. This is what. Okay, now what will happen? Next step, now bromide is going to be introduced here. Platinum is in +1 state here, so platinum is +1 state, and you can see here PR PPH3 PPH3. This I am going to get. Okay, okay, and again I am going to get plus PH CH2 radical, like this. See, again this hydrogen, whatever abstracted here, again it will go to this here. Okay, again it is going to form PH CH2 radical, PH CH2 radical, and this bromide radical, what is there, it will attach here, like this. Again I am going to get this complex here. It's like it's like a, what is say, +1 state here. Platinum will be +1 state, so it's like a chain. That's why it's called radical chain mechanism. Okay, like this. Now this is one PHCH2.1, and this is a fast reaction, and this is a fast reaction, and ultimately I am going to get platinum 2 CH2 PH Br P PH3 P PH3 like this. So now this is a fast reaction after this. Okay, this is a fast reaction, and finally I'm going to see that this radical whatever has been liberated here finally, that is CH2 radical PH is going to attach here CH2 PH radical. Br is already there, and these two PH3 PH3, so like this PH3 PH3, and from +1 it has changed to +2 like this. Okay, so this type of mechanism where the radicals are formed, again they are going to involve in this type of in the complexes like this. Finally from this introduction, that is pH CH2 Br, so both we have introduced here, so Br also is there and CH2 PH also is there. See, so how they are going to has introduced into this by the loss of two complex here. So we started with this, okay, and we added with 2 here. So that is what it has proceeded through the non-chain type of radical. So formation of the radical is there, and we can see that it has been happening. That's why this type of mechanism we can say that it is happening from the radical mechanism. This is the third type. Okay, one more type is the chain. So this is a non-chain. So in chain, okay, in chain type of this one, so it has been shown that the addition of ethyl bromide in this compound IrCOCl PMe3 twice Oscar's complex, but only thing is PPH3 PMe3 twice is been taken here. So Ir is in +1 state here, Cl PMe3 CO PMe3, okay, PMe3 twice like this, PMe3 COCl. So this is IR. So this is what first we are taking this complex, then ethyl radical. So in the presence of this we are seeing that it is in the presence of light or something, we are seeing that ethyl is been formed with the radical here, and the first step you can see ethyl will attach here like this. Okay, and here we get PMe3 COCl PMe3, this complex I am going to get here. So this is radical is being introduced here, and in the next step you can see here, so bromide, so this becomes a radical in this way. Okay, in the next step you can see bromide is introduced, IR ET PR CL COCl PMe3 PM like this. Okay, plus ET radical. So this type of it goes on, so that's it forms a chain. So again it is there, again it will introduce, then Br will be out like this. So this type of reaction where the chain is going to form. So here we got ET radical, again one product we got, so like this Br, again ET radical we get, again one third product will get, again ET radical, so like this. So ET radical, Br radical, so this go on forming the chain type of mechanism, and this type of complex is turning up. So this type of this we call it as a chain. Okay, chain type of mechanism here. So where each and every step you can see the radical is been out here, but in the non-chain you can see that there is no as such radical is present at the end. So all both the radical is introduced here, that is in the non-chain, but in the chain you have to show the final product as one of the radical here, ET radical again here. So we start with the radical here and we end up with the radical again here. Okay, and this will happen this way, that chain is going on to proceeding in this way. Okay, and this is how this type of mechanism we call it as a chain mechanism. Okay, and finally one more mechanism is there, that is ionic mechanism. This, okay, so radical mechanism or concerted SN2 and ionic mechanism here. Okay, so in the ionic mechanism the best is the addition of HCl. So this is what, okay, so we'll start with this complex PT PT P PH3 PH3 P PH3 P PH3. Okay, platinum with 4 of the PPH3 here, and now what will happen, H plus, so that is the addition of H plus with one of the PPH3 is out here. So I am going to get PT H, I will write here, so P PH3 P PH3 P PH3, I am going to get this one. Okay, so one of the PPH3 is displaced by the hydrogen here, and I get hydrogen here, and with all these three pH3 intact. Next step is what? Plus Cl here. So again one pH3 will go and one chloride will be attached, and finally I'm going to get PtCl H P pH3 P pH3 like this. Okay, so this type of now where H plus Cl minus both is been ionized here, and you can see that ionized product has been added here. So when it PPH3 is been out here, so with the giving the electron here, so what will happen, it will attach the one of the H plus ion here, and it is going to form this product. Okay, and what will happen now in the second product, the same PPH3 will be dissociated here, and positive charge will be created on this platinum, and that will be attached by the next, that is Cl minus here. So like this. So like this, in this type of dissociation type, in this type of mechanism where HCl is been dissociated, is been ionized here, and you can see that it is attached to this complex. So such type of mechanism we call a mechanism is a ionic mechanism. So like this, four different types of mechanism for the oxidative addition we have come across. That is, your first one is concerted mechanism, then second one is ascent mechanism, third one is radical mechanism. In radical, two types, chain and non-chain, and last one is ionic. Okay, in which this two is very much important. So make a very nice understanding for this two. This also is extra thing we have learned, so keep in the mind here. So this also will help you in some of the competitive examinations. Okay, now coming to the next some of the concept for the reductive elimination. Okay, so for reductive elimination, mononuclear. So binuclear, how we have learned. So similarly, so mononuclear will become, where the reductive elimination, we say this is what we get here, saturated compound linear AB. So what will happen now here, LNM plus AB like this. So mononuclear. Okay, this you keep in the mind. So this is what, and if you see the binuclear type of reductive elimination, same thing here. So one electron change and the two atoms will be seen here. So binuclear reductive elimination, if you see this, same thing here, one electron change will be there as we have done in the oxidative elimination. So here also you can take it like this, LNM A, and here it is M. Okay, so when this happens here, what will happen here? So there will be formation of LN M double bond like this, LN, okay, plus AP like this. Okay, so this type of this we call as a binuclear reductive elimination, where this is eliminated and you are going to get a double bond here. Okay, and one electron is shared between two metals, and this is been eliminated. So this type of mechanism we call it as a binuclear reductive elimination. Okay, binuclear reductive elimination. The best example for this we can give for osmium. Okay, so like this. So you can take 1 2 3 4 CH3 1 2 3 4. Okay, so this is a compound osmium 1 2 3 4 5. Okay, H is here, and here 1 2 3 4 5 CH3 is here. Okay, and this is a compound like we have taken here for binuclear. Now when you treat this with heat or light here, so what will happen now, as we have shown for binuclear here, so this being a cis here, they get eliminated like this. So I can write here minus CH4, methane CH3 plus H. So CH4 is eliminated, and you get here what, double bond here, and you get here like this osmium, and other things will be like that, 1 2 3 4 1 2 3 4 with carbon like this. Okay, so here elimination is what, methane gas, CH4 is eliminated, and you get this compound. And this type of reductive elimination we call it as a binuclear reductive elimination. Okay, so like this. So hope you understood this, some of the other concepts of this oxidative addition, reductive elimination, migrations. Okay, so like this. So let me see again few more, if I get some concepts very important pertaining to the competitive examinations or the examination point of view, I will collect and we will discuss this before going to the catalysis part of the organometallic chemistry. Thank you.